Hey guys, so today is Module 1, Day 13, Wednesday, and we're talking about some identities today, and we're going to do some simplifying and evaluating like we were before. Things are going to look just a little bit different, but knowing these identities will help us start to get a handle on things. All right, first off, identities are always true, okay, but for only real values in the domain of the variable. So you know what that means? That means they're true. We can take them to the bank. They're always true. And the reciprocal identities are going to be the sine of theta is equal to 1 over its reciprocal, which is cosecant of theta. Okay, and likewise, the cosecant of theta is 1 over the sine of theta. Then we have cosine of theta, which is 1 over secant of theta. And the secant of theta is 1 over the cosine of theta. They're reciprocals. And then tangent is 1 over the cotangent of theta. And cotangent is 1 over the tangent of theta. Okay? If I'm going too fast, just pause it and fill in your notes. I'm going to keep going for the sake of the video and time. Our quotient identities are basically, remember, quotient means division or a ratio, a fraction. So our quotient identities are tangent of theta is equal to sine of theta over cosine. And if you recall from the last time, or last week's notes, that sine is really a y value and cosine is really an x value. So it makes sense that our tangent is the sine over the cosine. And the reciprocal of tangent is cotangent, so that would be the cosine of theta over sine of theta. So you've got our reciprocal identities, and you have our quotient identities. The next thing we're going to talk about is our Pythagorean identities. Pythagorean identities comes from the Pythagorean theorem. Okay? So where does it come from? It comes from Pythagorean theorem. And if I have this triangle, okay, and let's say my radius is 1, like in the unit circle, then this is my x value, and this is my y value, my vertical change. Well, if I use Pythagorean theorem, or I set it up using these values here, I end up with x squared plus y squared is equal to 1 squared, which is 1. And we also discussed that x is really a cosine value. Okay, so we have cosine squared, plus y is really a sine value, and that equals 1. Now, this is an angle in here, and this is an angle. It looks really bad. Let me rewrite that. Okay, so we've got cosine of an angle squared plus sine of an angle squared is equal to 1. And then up here at the top, make a note that sine of theta squared is going to look like sine squared theta. It represents the exact same thing. So our first identity is going to be sine squared theta plus cosine squared theta is equal to 1. Now, other ways that you might see that is if I'm trying to solve for sine or I'm trying to solve for cosine. So if it was that I wanted sine squared theta by itself, then I would subtract the cosine squared theta. So 1 minus cosine squared theta. And if it was that I wanted cosine squared theta, then I would just subtract the sine squared theta. So you may actually see these and have to substitute certain values or certain expressions in for sine squared theta or cosine squared theta. All right, the next Pythagorean identity comes from the original. So let's take sine squared theta plus cosine squared theta equal to 1. And we're going to go through and divide everything by sine squared theta. Remember, what you do to one side, you do to the other. So this is really just a transformation almost of the same exact identity right here. And then we talk about sine squared theta over sine squared theta. Well, that's 1. Plus, then we have cosine squared theta over sine squared theta, which we saw was a quotient identity, and that was cotangent squared theta. And then 1 over the sine squared theta. And remember, that's not a 2 theta, that's sine squared theta, is going to be cosecant squared theta. That's our second identity. Other ways that I might want to see that or use this, if I want just 1, maybe I want to transform an expression to equal just 1, then I would subtract the cotangent squared theta from cosecant squared theta. And if I wanted to just solve for cotangent squared theta, then I would take cosecant and subtract 1. And that allows me to solve for cotangent or 1. Okay, the third identity, I'm going to start with the original, sine squared theta plus cosine squared theta equal to 1. And I'm going to divide each of those by cosine squared theta. And then I have a quotient identity here. Sine squared theta over cosine squared theta is tangent squared theta, plus cosine over cosine is going to be 1. And 1 over cosine squared is going to be secant squared theta. And then other ways that I could see that, I could solve for 1 again, and that's going to be by subtracting the tangent squared theta. So I have secant squared theta minus tangent squared theta. And maybe I want to solve for tangent squared theta. Well, that's going to be secant squared theta minus 1. All right, so these are just other ways that you can see how the same identity is used, but just manipulated to look like something else. Pythagorean identities. All right, just to throw this out, I can actually use Pythagorean identities to help me solve for certain angles. So let's take angle being pi over 3. Okay, so we'll call this an example. If my angle is pi over 3, then the sine of pi over 3 is going to be, well, there's my unit circle. Pi over 3 is here, so the sine is the y, square root of 3 over 2. And the cosine of pi over 3 is going to be 1/2. Well, if I use my Pythagorean identity, cosine squared theta plus sine squared theta equal to 1, then that's really cosine of theta squared plus sine of theta squared. That should equal 1. When I substitute those values in, cosine is 1/2, then I square it, plus the sine is the square root of 3 over 2, and I square it. That should equal 1. 1 squared is 1, 2 squared is 4. Square root of 3 squared is 3, 2 squared is 4, and 1 equals 1. And so I have verified that these values are indeed correct for pi over 3. And the Pythagorean identity shows me that that is very true. Okay? All right, so here's an example. We want to find the exact values of the 6 trigonometric functions of the angle theta shown in the figure. Now, this is just a random triangle. This is not in a coordinate plane, so there's no negative x values or no negative y values. We just have to find all 3 sides of the triangle and set up these ratios. Keep in mind this word exact. It means leave it in a radical, leave it in a fraction, or leave it with a pi. There is no approximation here. So decimal answers are not allowed. So let's put that, no decimals. Okay, sine. So we know sine is going to be O over H. We know cosine will be A over H. We know tangent will be O over A. Cosecant is the reciprocal, so I need H over O. Secant is the reciprocal of cosine, so H over A. And cotangent is the reciprocal of tangent, so A over O. And here is my angle. I have the O, I have the A, but I do not have the hypotenuse. So I know that Pythagorean theorem states that I can take the two legs, square them, and add them together. 3 squared plus 15 squared is going to equal my hypotenuse squared. So all I have to do is take the square root of that. Now, when I plug this in my calculator, I'm going to get a decimal, which means it's irrational, and I most likely have to simplify this radical. So I would say go ahead and add the radicand. That's what's inside the radical. 9 and 225 is 234. And then you have to ask yourself, can it be simplified? Well, can 234 be divided by 4? Can 234 be divided by 9? Can 234 be divided by 16? And so you go through and you check to see if any of these perfect squares are a factor. And in fact, 9 is. So this would be the square root of 9 times the square root of 26. Okay, when that simplifies, I get 3 square roots of 26. So my hypotenuse is 3 square roots of 26. Now I set up my ratios. And keep in mind, we've got to simplify. So if it's illegal, meaning a radical in the denominator, then we've got to change that. So sine is opposite over hypotenuse. So that's going to be 3 over 3 times the square root of 26. Well, that can be simplified to 1 over the square root of 26. And as we have found recently, that when I have values like 1 over the square root of 2 or 1 over the square root of 3, I always end up with the square root of 2 over 2 or the square root of 3 over 3. So following that pattern right there, when I simplify the sine, I will get the square root of 26 over 26. Okay, and then the reciprocal, the cosecant, well, I can just look at this and do the reciprocal, the square root of 26 over 1. Cosine is going to be the adjacent, which is 15 over the square root of 26, 3 square roots of 26. I can go ahead and reduce that out, and I get 5 over the square root of 26. Now, I can go ahead and do the reciprocal, that's the square root of 26 over 5, but I do have to simplify this. And likewise, same thing is true that was here. I just multiply it by 5. So 5 times the square root of 26 over 26. Okay, tangent is the opposite over the adjacent, which is going to be 3 over 15, which reduces to 1 over 5. And then the cotangent is the reciprocal, so that's 5 over 1. And so we have found all the exact values of the 6 trigonometric functions for this triangle here. Again, this is just a random triangle somewhere on a paper. So trying to find all those values, like negatives and positives, these are all positives. When it comes to a coordinate plane, those are going to have negatives.